Next, let's look at page 116, the subsection 7.3 of chapter 3, Mercator maps. What it is let's say you have a sphere, okay, like the Earth that we live on, but we need to draw the map of the world, and we can't do it on a piece of paper. So what we're gonna do is translate the sphere into a cylinder, and then unroll the cylinder so it becomes flat. Now, in doing that, of course, some things are going to be distorted because it's not practically possible to flatten the sphere into a cylinder. Okay, something's got to give. So so here's the plan we have. What we're going to do is wrap a sphere, that's the Earth. Okay, we're going to wrap it tightly with a cylinder, like with a piece of paper or something, clear around it so it's tangent, so that the two objects have the same radius. Okay, but this is a cylinder, and inside we have a sphere wrapped inside, and we will translate each point on the sphere onto the cylinder in this way. Now, first, we have two angles. Okay, here's what your book says on the same page. We have two things to think about for the sphere. We have theta, of course, and then we have phi. Okay, and each point on the sphere is determined by those two values. So to translate any random point, such as p, from sphere to cylinder, we are going to preserve the theta, because the cylinder just needs theta. Is defined by theta and z. Okay, z is the height, or the height of the cylinder. That is done in the previous page. Okay, the coordinate of a cylinder, as you can see, is determined by theta and z. This is the previous page. Okay, 115, right here. See, theta and z will determine the position at any point on the cylinder, given the radius is a. So then we're going to translate it, and how are we going to do that? Well, we'll keep theta, but what about phi? We're going to change phi in such a way that the point P, say, a random point P on the sphere, will be translated to point Q on the cylinder in this way, in such a way. Okay, now please read this part carefully, where it says that in such a way that the angles of any curves on the sphere will be preserved when that curve get translated on the cylinder. So then the angle, that is its slope, will stay the same. And then being that theta is the same in both cases, then we only have to worry about determine z, okay, as a function of phi. So as long as we figure out how z should relate to phi, then we will be able to come up with this translation. Now, notice specifically that it's not such a simple matter as you simply draw a straight line from the origin of the sphere or center of the sphere to P, and then extend it all the way to the cylinder, and that gives you a point called R, but that's not our point. Okay, our point is some other point in such say Q, in such a way that any curves that being translated will have the same slope at any point, compared to what it used to have with the latitude. That is, however much is slope before on the cylinder, it will have the same slope. And the reason we want that, well, because we want our map to be conformal. Okay, so that is the only condition. Now, knowing that, then being that phi is the same, we don't have to think about it very much. So the only slope we have to worry about is the slope between the old slope, which is on the cylinder, and the new slope. The old slope on the sphere and the new slope on the cylinder have to be the same. Now, in the previous page, okay, we see that the old slope is given as 1 over cosine phi d phi by d theta. Okay, and the new slope down here is is 1 over a dz by d theta. And we're going to put those two slopes the same. Okay, this is it. Here's our equation. We're going to solve this equation, and this differential equation, and whatever the answer is, will be our relationship between z and phi in the cylinder, and that will give us the transformation. And as you can see, it just happened that we already solved this differential equation. Okay, look at it carefully. And where have we seen this before? We saw it in the previous page, where we were doing the loxodrome. Okay, the loxodrome had just happened to have an almost exactly the same differential equation where where theta, where is it? Well, anyway, there's this thing which is a similar, if not identical, differential equation. So which we solved at the time equal to this thing, and therefore it's the same situation is happening here. Okay, we have, see, this is the solution to this differential equation is also this. We don't even have to do it again. It's the same deal. So now that we know how we're going to translate phi into z, and then theta will stay the same, so now we got our translation all figured out. And as an example, as if you look at the bottom of the page, then you might have a point, okay, with latitude 45, longitude 45 degrees, latitude 30, and then if you plug in this formula, theta stays the same, so theta is still 45 degrees. Z, you got to plug it into that equation, and quickly you will come up with that answer. Please do that yourself, okay? And then, so that is the thing on the cylinder. Now, what happens when we unroll the cylinder, so it becomes the plane map, then all we have to do is x. We just change the x coordinate. The x then equals to a times theta. If you think about that, that's pretty obvious, okay? And so spend some time think about that until you realize why that is. And then y will be the z coordinate, which is whatever that is. And that will be a translation of things getting onto the xy plane. From the sphere. So as a result, that is what the Mercator map is. It translates things from the sphere all the way into the cylinder. And so that is about that. So please confirm that that little example there yourself, okay? Make sure everything comes out. Now I want to mention that you notice that the transformation has a tangent in there, okay? Now eventually, as we do homework, you will realize that as the points that we translate reach getting closer to the North Pole or the South Pole, the tangent is going to shoot up to huge, way up there on the cylinder. So as a result, this map is only practical up to, I would say maybe 45 degrees, maybe 50, because after a while, your map is way up there. It just doesn't make any sense to draw it that way. But up to say 45 degrees or so, maybe 50, the map, you can get the map to be reasonably sensible and to do that. So with that, that is the end of this section. Please do homework. Let me show you the homework. So for homework, please do page 117. Please do problems 1, 5, 7, 9, 10. For problem 10, please graph it on the Desmos 3D calculator if you can. You don't have to, but it looks really neat. So I would like you to try to play with it if you could. And then problem 11, 12, again, please graph 12 if you can, because it's great fun, okay, and to do so. So please go do your homework, and when you're done, I want to talk about it. So let's first look at problem 1. I think it's just a straightforward calculation of something, okay, not much worth mentioning. So we'll just follow the formula. I just followed the formula of ds by d theta and plugged it in and got the same answer as the back of the book, and that should be okay. All right. So next, let's look at problem 5, where we calculate the length of some loxodrome. That sounds more interesting, okay? And so the loxodrome is defined as given as this formula, okay? And then so by following that formula, then I calculate what d theta is in terms of d phi and just plugged it into the distance formula. And in doing so, you notice that something very convenient happened. The cosine square phi canceled itself out so that when I do integration, I'm only integrating some constant. Okay, so therefore the answer to the integration popped out right away. And this is the same as the back of the book. So I take that to mean that I'm right. Now notice that in the answer, the loxodrome has a finite length unless lambda equal to 0. Okay, then the length goes to infinity. And that's because, well, the loxodrome it goes around, and as you get to the top of the sphere, it t just, it doesn't ever get close. It just, it's a limiting situation where it just spins around forever. But nevertheless, the length is still constant. Yeah, I mean, the length is still limited, okay, that you can calculate it from the integration, unless the lambda equal to 0, in which case you just go around the equator forever, okay, and so that, which then you can, and then this length goes to infinity, being that you're just going around the equator all the time. And so that's problem 5, and problem 7 is just a quick, simple thing where the loxodrome on the cylinder, that's just the straight line, okay, when you unfold it, and with a set slope or something, and the length is the length is just the Pythagoras theorem, okay, so that comes out right away, I believe. So next let's look at problem 9, a curve theta equals to phi, a simple one, okay, and we are transformed by the Mercator projection onto the cylinder and the n on the plane, and we need to know what are the transformed curves look like. Okay, so I think this is a fairly short problem. I have you just basically write down what the formula that the book shows. So the cylinder will be something like that, being the theta equals to phi, just plug it right in. And then on the plane, similarly, basically it looks about the same thing. All right, so now that is a quick answer. And to make sure that I got it right, what I did is I plotted this thing into the Desmos calculator. As you can see, here are the formulas I typed in. Okay, first the green one is on the sphere, and then the purple one is on the cylinder, as you can see, and I have 2 points on there to show you the transformation. That green point is something, okay, and which is translated into the green point on the sphere is translated to the green point on the cylinder, and then the orange point on the sphere is translated into the orange point on the cylinder. As you can see, the higher you go, the closer to the North Pole, the higher that projection on the cylinder is going to be. Now, and I also have this plotted with the cylinder intact, so you can see it better, okay? That's a curve, the purple curve really is on the cylinder, right? And this is the exact same view, except that I clicked on the cylinder, so you can see it better. But as a result, you can't see the dot on the sphere as much. But yeah, so please plot this yourself if you want to play with it and move it around and see where the dots are and stuff like that. And then finally, the formula on the plane, when you unroll the cylinder, you see that the formula on the plane looks very similar to it looks, very close to this one on the cylinder. Being that the plane is well, the cylinder is just the plane rolled up, so so it looks everything looks about right. So that is that's that. Now next, let's look at problem 10, where we're gonna do a real story of a ship sailing. So a ship sails northeast, okay, from on the Earth from point theta equals 45, phi equals to 15. To following the compass, so it's preserving angles. It's preserving the direction, cutting all meridian at the same angle of northeast. Okay, now first we need to figure out what does that mean. Now, if from geography, high school geography, you might remember that the term northeast is defined as the exact middle point between north and northeast, okay? There's north, there's east, the 45-degree direction is northeast, and then the one right smack in the middle is called northeast, which end up being 3 pi over 8 in terms of angle, measured from the x-axis. So then, so we know that, so the angle being 3 pi over 8, and we will, so at that point we'll just plug stuff into the formula, and we need to figure out what the constant is in the formula, okay? So I did some work here, which eventually I came up with a constant equal to that stuff at the bottom. Continuing, I did I don't know what I did. And anyway, so I'm messing with various constants to get the formula to come out, and eventually it did. And here's the formula on, right here, okay? The underlined one, here's the formula on the plane. And that, I believe, is what we're shooting for. And then the formula on the sphere is this thing, which I wrote it out later because I wanted to plot this thing into the Desmos calculator so that I can look at it. So that's so let me show you what I plotted. Oh, I forgot to show you something in the previous problem. That is, as I mentioned, that if your point is too close to the North Pole, then your projection on the cylinder is going to be very high up, as this example shows. You notice that for the orange dot, okay, which is close to the North Pole, the corresponding point on the cylinder is way up there. So yeah, that's that. So coming back to problem 10, we have, see, there's the graph I plotted on the Desmos 3D. The path on the globe, as you can see, the ship is sailing aiming practically pretty much towards the north, right? So it's heading, well, straight towards the North Pole, practically. So as you can see, the ship is getting very close to the North Pole, and its corresponding path on the cylinder looks practically like a straight line. Now that is an okay demonstration, but I feel that is not good enough as to showing what does the loxodrome look like. I mean, it's too far north. I want to see what the loxodrome look like when it's not looking too much north, when it's winding around the globe a little more. What does the map on the cylinder look like when that happens? So here's what I have. So here is I plotted a different loxodrome, this time with a much smaller slope, so that it winds around the Earth a couple more times. And here is what I have. See, the corresponding points at the orange point, that's the starting point. As you see, both paths start at the same point. Now, the next point, you can see the two are almost coinciding, right? But as it goes on, however, the one on the cylinder start looking a bit off. See, here's the orange point. You probably can't see it very well, but it's becoming to lag behind a little bit. And the end point, these are the 2 points. As you can see, it's starting to lag behind. The blue ones on the cylinder is lagging behind quite a bit compared to the one on the orange point. But they are the corresponding points. And so let's see, I recommend, let's see, did I ask you to graph this? Yeah. And here are the details of how I graphed it, in case you run into any trouble as to the graphing. In the graphing, the t represents phi in this equation and theta in that equation, because one is on the sphere and the other one's on the cylinder or something. Yeah, so that should be enough information in case you need. Yeah, so that should do it, and that's that. So next, let's look at problem 11. We have the angle between the curves on the sphere. Okay, okay, we have two curves. We're figuring out the angle of the intersection, and then we need to find the angle at the Mercator map, okay, at the same point. Well, we know the angle is the same because Mercator map, by definition or by its description, is preserving angles, so they will be the same. So all we need to do is find out the angles of the intersection of these two curves on the sphere, and then we're done. So to find that, we will well, we have given the calculation. Okay, we need to figure out where the curves intersect. So we'll set these curve 1 and curve 2 to be the same. Solve for theta, and I got theta equal to 1 or theta equals to -2. And we'll just do the math for those two and not think too hard beyond that. Okay, so first, if theta is 1 and so on, and we calculate the angles and then calculate the difference, the intersection, then the intersecting angle of where I end up figuring out to be 43 degrees, which when I check the answer at the back of the book, it is correct. Okay, and then after that, well, anyway, so after that I calculate the second angle the same way, right? We crank out the tangents and then do the difference of the angle, and it is correct. Now at this point, let's look at the answer at the back of the book. And you notice that the answer at the back of the book is long and cryptic, okay? It's this stuff. These are the two angles it calculated. Now, if you punch this out on the calculator, it does answer to be exactly what I have. Okay, we do this, that is, we found the angles from their tangent form, calculate the difference, and then get out the answer. But where did the book get this thing? This comes from the formula of, there is a formula, okay, for tangent inverse. That is, here's a formula that says the tangent inverse of arctan of A minus arctan of B equals to this, okay? So if you plug that into the formula, it does come out that that both situation, it does work, okay, which is why our answer is the same. But that's where the book got the answer. They end up using this formula to get, that's where they got their answer out of. So so that's that. If you don't remember that, it's not a big deal, right? I don't remember the last time I did arctan difference of angles. Ugh, I don't even remember this thing. But anyway, it exists, and that explains why the book's answer looks somewhat cryptic. And oh yeah, I better not forget to show you the drawings. I plotted this answer onto the Desmos 3D. Here's the first angle where theta was what, 1 or something? What was it? Whatever it was, this is the first angle. Okay, as you can see, the two angles at the red dots, they look identical. They better be, okay, and it looks about 43 degrees. And then the second angle is at the bottom. You can see it even on the, see the bottom dot, orange dot down here? It's kind of hard to see, but that's the second intersection. So I moved over a little bit. Okay, here's the second graph is looking at it from the bottom. And you can see the second angle, it intersects, and it turns out to be a much smaller angle than the first one. Yeah, so that's that. Next, problem 12, where we have a very interesting situation called central projection, where we're going to carry a point P on the sphere, shoot it through the sphere and the center of the sphere until it hit the other side of the cylinder. And then if we do that to every point, okay, and then we're going to prove that if we did this kind of a mapping, it will not be conformal. That is, it will not preserve angles. Now, and as a sample, we'll consider some curve that goes through the point theta equals to 0 and pi equals to phi equals to pi over 4. So I drew a simple picture here. Okay, here's our original point P, and there's our sphere, and the two lines are our cylinders. And I'm going to shoot P through the center of the sphere, clear to the other side of the cylinder, and that is projection point. And we're going to do that for every single point on the sphere. Okay, and then of course you can argue that at the North Pole you can't do that because it will just shoot down to infinity. But any point that isn't on the North or South Pole, you can theoretically do this. Okay, just shoot it through the center until it gets to the cylinder somewhere. And as you get close to the North Pole, you're going to shoot way down, right? But it's theoretically doable. So anyway, so we're going to do that, and we're going to calculate two curves. So for the first curve is lambda equals to 1, and I think that's the one that was given, right? Let me see, is that what's given? Yeah, we consider a curve on the sphere passes northeast. That means lambda equal to 1, right? The slope is 1, and so that's the first curve. And then we have calculation on the cylinder, then the corresponding point after some calculations, you quickly realize, we'll assume the sphere's radius to be 1 unit, okay? 1 Earth radius unit, we don't care what the unit is. It's the same principle. And so we'll assume A is 1, so that on the cylinder, the location of the corresponding point from P will be pi comma negative 1. And then if we were to calculate the slope of it by, I don't know, plugging in some numbers where phi is pi over 4, 4, and so on. We will eventually, here's what I did, but eventually we'll calculate the dc by d theta, that is the slope on the cylinder of the corresponding curve is going to be square root of 2 instead of 1 like this curve on the sphere, and therefore the map is not conformal. All right, let me show you that again so you can see the whole thing at the same glance. That's good enough. And so let me show you what I plotted on the calculator. On Desmos 3D, we have, okay, so here is my my thing on Desmos 3D. As you can see, the purple point on top of the sphere, that is the original point P, okay? And then I drew a curve. That's the curve with a slope equal to lambda equal to 1. That is, the slope is 1, a 45-degree angle on the sphere. And then we shoot it from the point, shoot straight through the center of the Earth and down across the sphere, through the sphere on the other side until it hit the cylinder at the orange point. See? And then not just that, the point, but the entire green curve over there got mapped to the what is that color? Red, I guess. The red curve on the bottom. You notice that what's on top will be shot down to the bottom. That is, the part of the curve that's on top towards farther north of the purple dot on the sphere will go down to the, because it's going through the center, so it will go down to the southern part of the red curve. Anyway, so as you can see, the curve will shoot right through. Okay, and if you plot this thing and draw the line in the middle, see, and I got rid of some part of the graph on the cylinder and the sphere so that we can see inside better. And over here I took a screenshot of this thing on the other side. I turned it around and looked at it on the other side, so it looks like this. And then I superimposed it with the graph y equals the square root of x to make sure that, see, the superimposing show that my calculation is very likely correct because they are exactly the same, the slope is, to make sure that I didn't mess up somehow. So that is, it looks quite neat, okay? And then I also want to show you how I plotted all this stuff. Here's all the equations that you might need. As you notice, the graphs, the curves, the green, the green one is the one on the sphere, and the orange one is the one on the red one is on the cylinder, I think, and the t in here, one represents phi, the other one also represents phi, I guess. Well, anyway, so that's how you do it. They look very long, but mostly you can just copy and paste, which is what I did. So it didn't take near as much typing as it looks here. Yeah, so that is, that should be that. So it's a very nice problem, I thought, where you can shoot, especially because I can plot this thing on the Desmos calculator. Look how beautiful that is. I'm very proud of this graph, okay? And especially because they let me get rid of some of the graphs so we can see inside. Otherwise, you have to see through this thing, and then everything be blurry and you can't see what's going on. Anyway, so that is the end of this section.